Our universe is governed by two rulebooks that cannot agree. One book, Einstein's theory of general relativity, masterfully describes the cosmos, from orbiting planets to the bending of light around black holes. The other book, Quantum Mechanics, reveals the bizarre and probabilistic world of atoms and particles. Each theory is stunningly successful in its own domain, yet they are fundamentally, mathematically incompatible. This conflict creates the greatest puzzle in modern physics, the search for a theory of quantum gravity. By the end of this exploration, you will have a clear map of 30 distinct paths physicists are taking to solve this ultimate mystery. We will see how some theories propose hidden dimensions, while others suggest space and time are an illusion built from quantum information. What does it feel like to stand at the edge of such a profound unknown? To bridge this cosmic divide, physicists have proposed a breathtakingly elegant idea. What if the universe's fundamental ingredients are not zero-dimensional dots but tiny, vibrating loops? This is the heart of string theory. In this radical picture, every particle we know, from electrons to photons, is not a point but a one-dimensional string, unimaginably small. The only difference between a particle of matter and a particle of light is the note or vibrational mode that the string is playing. A string vibrating one way might be an electron, vibrating another way becomes a quark, and a specific, harmonious vibration would produce the graviton, the long-sought quantum carrier of the gravitational force. In one sweeping vision, string theory aims to be a true theory of everything, weaving all forces and all matter into a single, unified tapestry of vibrating strings. Yet this profound elegance comes with a profound cost. The mathematics of string theory only works if our universe has more than the 3 spatial dimensions we experience. It demands a symphony played not in 3 dimensions but in 10 or even 26. The extra dimensions the theory suggests are curled up and hidden at every point in space, too tiny for us to perceive, like the intricate, compacted threads within the weave of a carpet. Yet string theory's vision of hidden dimensions is not the only path through this quantum wilderness. A radically different approach asks us to question the very stage upon which the drama of physics unfolds. What if gravity is not a force to be unified, but a direct manifestation of space and time's own quantum nature? This is the powerful premise of loop quantum gravity. While string theory adds new dimensions, loop quantum gravity takes our familiar 4-dimensional spacetime and breaks it down into its most fundamental, indivisible parts. It proposes that space itself is not smooth and continuous like a perfect sheet of glass, but is instead woven from an incredibly fine fabric of tiny, interwoven loops. Think of the fabric of reality not as a blank canvas, but as a vast dynamic network of connections, like an unimaginably complex spiderweb where each thread is a line of gravitational force. These loops are the quanta of space, the smallest possible units of area and volume. This means there is a limit to how small a piece of space can be divided, a fundamental granularity to the universe. At the unimaginably tiny scale of the Planck length, spacetime would no longer be serene. Instead, it would churn with a turbulent, ever-changing geometry often called quantum foam, where the very concepts of here and now lose their smooth meaning. In this view, the smooth continuum of space and time is an illusion that emerges from this underlying quantum network, much like the smooth appearance of a television picture emerges from countless tiny, discrete pixels. So we have two profound yet opposing visions. One weaves gravity into a symphony of strings in a higher dimensional realm. The other suggests that gravity is the quantum hum of spacetime's own granular structure. But there is a third path, one that approaches the problem like a cosmic architect. This framework is known as causal dynamical triangulations, and it asks a beautifully simple question. What if we could build spacetime from the ground up, piece by tiny piece, to see what naturally emerges? Instead of strings or loops, this theory starts with the simplest possible geometric shapes, tiny triangles, or their higher dimensional cousins called simplices. Think of these as the indivisible Lego bricks of reality. The rules of the game are strict. Each tiny triangle must connect to its neighbors in a way that respects the fundamental arrow of time, the principle of causality. This means every connection has a clear before and after, ensuring that cause always precedes effect, even in the quantum foam. The theory then uses the powerful tools of quantum mechanics to sum over every possible way these triangles can be glued together, exploring a vast ensemble of potential universes, each a wildly different, crumpled geometric shape. This is the quantum superposition of spacetime itself. The breathtaking result is that when you apply these quantum rules to this cosmic Lego set, something remarkable happens. Out of the frenzied quantum dance of all possible configurations, one dominant shape consistently emerges. It is not a chaotic, crumpled mess, but a smooth, four-dimensional universe that looks exactly like our own on large scales. From the bottom-up assembly of timeless, causal rules, the familiar flow of time and the expansive three dimensions of space spontaneously crystallize. It is as if you gave a child a box of chaotic, flashing lights, and by following a few simple connection rules, they accidentally assembled a serene and stable lamp. This approach does not assume large-scale spacetime. It derives it, offering a compelling story of how our ordered cosmic stage might naturally arise from the quantum chaos beneath. Yet another path emerges from the quantum thicket, one that seeks not to replace Einstein's masterpiece but to complete it. This approach asks a daring question. What if the problem of uncontrollable infinities in gravity is not a sign that general relativity is wrong, but merely that we have not yet seen its full, self-consistent form? This is the hopeful idea of asymptotic safety. To understand it, think of a river flowing down a mountain. The water represents the strength of gravity's influence at different energy scales. In most attempts to quantize gravity, this river becomes a raging, unpredictable waterfall as you approach the extreme energies of the quantum realm, drowning calculations in a flood of infinite, meaningless numbers. Asymptotic safety proposes a different destiny. It suggests that the river of gravity's strength could flow toward a stable, calm lake at its highest energies, a mathematical fixed point. At this fixed point, the theory's parameters become predictable and finite, no matter how deeply you probe. The infinities are tamed not by adding strings or granularity, but by the theory's own mathematical behavior. It is as if Einstein's equations, under the intense pressure of the quantum world, reveal a hidden, perfectly stable configuration we had not seen before. This would mean that general relativity, our trusted guide to the cosmos, could be a complete theory all on its own, valid from the orbit of planets down to the very fabric of spacetime. It does not require extra dimensions or a breakdown of spacetime, only a deeper understanding of its own quantum nature. So we now have a quartet of profound possibilities. Strings weaving in hidden dimensions, loops forming a granular spacetime, triangles building reality from causal rules, and the hope that Einstein's own equations might yet hold the key to their own quantum completion. The search is far from over. Perhaps the most minimalist vision of all suggests we strip reality down to its barest bones, forget strings, loops, or triangles for a moment. What is the one irreducible relationship that defines our universe? It is the simple, unbreakable chain of cause and effect. One event makes another possible. This spark ignites that flame. This thought leads to that action. Causal set theory builds the cosmos from nothing but this fundamental idea. It proposes that deep down, spacetime is not a smooth, flowing river. It is a vast, discrete collection of elementary events like individual grains of sand. Each grain is a fundamental point, a here and now in the most basic sense. And the only property these grains possess is a set of relationships, a cosmic ledger stating which events can influence which others. One grain representing an event either lies in the past of another or it does not. There is no distance, no geometry, no smooth fabric, only this immense growing web of causal connections. From this sparse, elegant starting point, something miraculous is meant to happen. The familiar four-dimensional continuum of spacetime, with all its curves and stretches described by Einstein, is not a foundation. It is an illusion, a large-scale picture that emerges from the collective pattern of countless causal links. Think of a vast pointillist painting. Up close, you see only individual, separate dots of color, but step back, and those dots blend seamlessly into a beautiful, continuous image with depth, shape, and light. The painting is not in the dots, it emerges from their relationships. In the same way, causal set theory suggests our smooth experience of space and time emerges from the intricate network of before and after linking the universe's most basic events. This approach naturally provides a fundamental limit to reality's resolution, a smallest possible scale, because the grains of the causal set are discrete and indivisible. There can be nothing between them by definition. It is a universe built not from stuff, but from pure relationship, from the immutable logic of cause and effect itself. But what if the universe's most fundamental geometry cannot be drawn on any map, no matter how granular? There exists a mathematical realm where the very coordinates of space rebel against the rules we take for granted. In our everyday world and in classical physics, the order of measurements does not matter. You can walk 5 steps north, then 3 steps east, and you will end up in the same spot as if you had walked 3 steps east first, then 5 steps north. The operations commute, yet in the quantum world, this simple commutativity breaks down spectacularly. The act of measuring a particle's position fundamentally disturbs its momentum, and vice versa. Heisenberg's uncertainty principle is a direct mathematical consequence of this noncommutativity. Now, a profound theory asks us to apply this quantum lesson to the stage of reality itself. Noncommutative geometry proposes that at the tiniest possible scales near the Planck length, the coordinates of spacetime themselves do not commute. Measuring one dimension interferes with measuring another. This is not just a limitation of our tools, it is a fundamental property of space and time. The result is a kind of intrinsic fuzziness, a quantum foam where the very notion of a sharp, pinpoint location becomes meaningless. You cannot say an event happened at an exact here and now because those concepts blur into one another. It is as if the universe's fabric is woven from a material that resists being pinned down to a perfect grid. This mathematical framework, deeply inspired by the formalism of quantum mechanics, suggests that spacetime itself has a quantum structure from the outset. One of the most tantalizing consequences of this fundamental fuzziness is what it might do to the most terrifying predictions of general relativity, the singularities. Inside a black hole, according to Einstein's equations, density and curvature soar to infinite values, a point where the laws of physics break down completely. But in a non-commutative geometry, this mathematical disaster may simply vanish. Because there is no such thing as an infinitely sharp point, matter cannot be crushed into a true singularity. Instead, the immense gravitational collapse would reach a maximum density and then rebound or stabilize, avoiding the infinite paradox altogether. The black hole's heart would not be a lawless void, but a region of extreme yet finite quantum fuzziness. This approach does not add new dimensions or discrete building blocks, but instead changes the very algebra of reality, suggesting that the smooth, classical continuum of spacetime is an approximation that melts away under extreme scrutiny, revealing a deeper quantum geometric truth. The idea that gravity might be an illusion is perhaps the most radical proposal on this list. We are used to thinking of it as one of the universe's fundamental forces, a basic ingredient woven into the fabric of reality. But what if it is not fundamental at all? What if gravity, like the pressure of a gas or the temperature of an object, is an emergent phenomenon? It would not be a force in itself, but a collective consequence, a large-scale mirage arising from the statistical behavior of countless microscopic parts we have yet to fully identify. This is the startling premise of entropic gravity or emergent gravity. To grasp this, consider a simple analogy. Think about the concept of temperature. If you could zoom in on a hot cup of coffee, you would not find a little heat particle inside. Instead, you would see a frenzied dance of countless molecules jostling and vibrating. Temperature is not a fundamental entity. It is an emergent property that describes the average kinetic energy of that invisible dance. It only makes sense when you have a vast number of components. Entropic gravity suggests that the force we call gravity is similar. It may not be a fundamental interaction but a statistical effect, an entropic force that arises naturally from a system's tendency to maximize its disorder or entropy. The groundbreaking work of physicist Eric Verland proposes a specific and beautiful mechanism for this. He suggests that the information content, the entropy, associated with the horizons of spacetime is the key. In this view, what we perceive as the gravitational pull of a massive object like a star is actually a consequence of the way that object changes the entropy of the microscopic quantum bits or qubits that make up space itself. Imagine space as a kind of cosmic memory system. A massive object, by its mere presence, distorts the way information is stored on this fundamental level. The system then responds by rearranging itself to maximize entropy, and this statistical push toward greater disorder manifests as an attractive force we call gravity. Even inertia, the resistance of an object to changes in its motion, could be reinterpreted through this lens. When you push an object, you are not fighting some intrinsic property of matter, but rather you are fighting against the entropy gradient of the underlying information structure of space. This framework provides a stunning bridge to another profound idea, the holographic principle. If gravity and space are emergent from information, then our three-dimensional reality with its gravitational forces could be a projection from a two-dimensional surface where that information is fundamentally stored. In this entropic view, a black hole is not a mysterious object with a singularity, but the ultimate entropy maximizer, a natural consequence of the information-theoretic nature of reality. It transforms gravity from a geometric warping of a pre-existing stage into a thermodynamic consequence of the stage's own quantum memory. We are not pulled by a force, but rather, we are moved by the universe's relentless drive toward disorder, playing out on the most fundamental canvas imaginable. This idea of gravity emerging from information leads us to one of the most startling revelations in modern physics. There is a principle which suggests that the universe, in a very literal sense, might be a cosmic projection, a grand illusion of dimension. It is called the holographic principle. To grasp its strange beauty, think of an ordinary hologram like the shimmering image on a credit card. That three-dimensional picture you see is not stored within a three-dimensional block of plastic. All the information needed to create that full, rich image is encoded on the flat, two-dimensional surface of the foil. The holographic principle proposes that our entire universe might work the same way. All the information that describes everything within a volume of space, every star, every planet, every person, could be perfectly represented or encoded on the lower dimensional boundary that surrounds that volume. For our cosmos, that boundary would be a vast, distant, two-dimensional surface. In this view, the three-dimensional reality we move through, with all its depth and solidity, is not the fundamental reality. It is a projection, a holographic movie playing out from data stored on a cosmic screen we cannot see. This is not science fiction, but a serious idea born from the deepest puzzles of black holes. In the 1970s, physicist Jacob Bekenstein made a revolutionary proposal. He argued that a black hole's entropy, which is a measure of its hidden information content, is not proportional to its volume as one might expect. Instead, it is proportional to the surface area of its event horizon. This was a profound clue. It suggested that all the information about what fell into the black hole was not lost inside its mysterious volume, but was somehow painted onto its two-dimensional surface. Later, work by Gerard T. Hooft and Leonard Susskind expanded this insight into a universal principle. If the maximum information a region of space can contain is limited by the area of its boundary and not its volume, then volume itself might be an emergent property. The true, fundamental degrees of freedom, the bits and pieces that make up reality, could live on a surface, and the interior we experience is a kind of useful, three-dimensional translation. What does this mean for our search for quantum gravity? It provides a breathtakingly elegant framework. It suggests that the quest to unify gravity with quantum mechanics in our three spatial dimensions might be asking the wrong question. The true quantum theory, the one that seamlessly includes gravity, might be a simpler, lower-dimensional theory without gravity at all, living on that boundary. The gravity we feel and the three-dimensional world we inhabit would then emerge holographically from the interactions described by that boundary theory. This is not just a philosophical idea. It has a concrete mathematical embodiment called the anti-de Sitter conformal field theory correspondence, which provides a precise dictionary translating problems in a warped space with gravity into problems in a lower-dimensional quantum field theory without it. While our universe is not exactly of that specific type, the correspondence stands as a powerful existence proof that such holographic descriptions are mathematically possible. It transforms our view of dimensionality itself. We are no longer simply beings living in a three-dimensional box. We are dynamic holograms, our entire lived experience a rich, interactive projection from a shadow world of fundamental information. The stage of spacetime is not given, it is computed. The holographic principle finds its most powerful and precise expression in a mathematical framework of breathtaking depth. This is the anti-de Sitter conformal field theory correspondence, often called the greatest gift of string theory to physics. It provides a concrete dictionary for translating between two seemingly separate worlds. On one side of this cosmic ledger is a special kind of universe, an anti-de Sitter space. Imagine a vast, saddle-shaped cosmos where gravity is strong and spacetime is warped in a particular, negatively curved way. Crucially, this ad-s space has a boundary, a distant, enclosing surface. According to the correspondence, the complete description of quantum gravity and all the strings moving within this entire warped universe is perfectly equivalent to a very different kind of theory living only on that lower dimensional boundary. This boundary theory is a conformal field theory, a quantum system without any gravity at all, where particles and forces interact but the concept of distance can be scaled without changing the physics. It is a perfect hologram. Every single process, every collision of strings, every ripple in the geometry deep inside the warped bulk of the ad-s space corresponds precisely to a specific event or interaction in the flat, gravity-free quantum field theory painted on its boundary wall. One language describes warped spacetime with gravity, the other describes a flat quantum dance without it. They are two different yet perfectly equivalent descriptions of the same reality. This is not a vague analogy, but a rigorous mathematical duality. Physicists have an actual dictionary where they can translate a complex calculation about the behavior of a black hole in the gravity side into a potentially simpler calculation about the thermal properties of a quantum plasma on the boundary side. This tool has proven revolutionary not for building rockets but for solving some of the most intractable problems in theoretical physics. For decades, certain quantum systems, like the soup of quarks and gluons that filled the early universe, have been notoriously difficult to study because their interactions are so intensely strong that normal mathematical tools break down. The add-SCFT correspondence provides a backdoor. By the rules of the dictionary, this messy, strongly coupled quantum soup can be mapped onto a problem involving gravity in a warped spacetime, where the geometry itself can be used to solve it. It is as if you had a fiendishly difficult lock, and this duality handed you a completely different key that somehow, miraculously, opens it. This has allowed researchers to calculate properties of these exotic quantum states with an elegance previously thought impossible, using the curvature of an imaginary spacetime as a computational guide. The correspondence stands as a monumental clue, suggesting that the search for quantum gravity might be fundamentally about translation, about finding the right language in which the universe's deepest laws become simple and clear. There exists a geometry so profound it seeks to rewrite the very language of physics. While many theories add new ingredients to reality, mathematician and physicist Roger Penrose proposed a different kind of revolution, one that changes the alphabet we use to describe the cosmos. This is twistor theory. At its heart is a deceptively simple shift in perspective. Instead of taking points in spacetime as the fundamental stage, twistor theory begins with light. Specifically, it starts with the paths of light rays, the null lines that define the causal structure of the universe, the very boundary between what can and cannot influence an event. A twistor is the elegant mathematical object that encodes this entire light cone structure. Think of it this way: in our ordinary view, we label an event by its four spacetime coordinates, a where and a when. A twistor, however, represents not just a point, but the entire family of light rays that pass through that point. It is a description that inherently contains the relationship between events, the causal connections that weave the fabric of reality. This shift from points to light rays is a move from a local, granular description to one that is inherently holistic and relational. The ambition of twistor theory is breathtaking. It aims to provide a new foundation where quantum mechanics and the geometry of spacetime are not separate puzzles to be forced together, but two aspects of the same, deeper mathematical structure. In this framework, the familiar four-dimensional spacetime of our experience is not the primary reality, but a secondary construction that emerges from the interactions of these more fundamental twistor objects. The quantum wave function of a particle, with all its probabilistic strangeness, finds a natural home as a geometric object in twistor space. It is as if we have been trying to understand a beautiful, intricate tapestry by only looking at individual threads. Twistor theory suggests we step back and study the pattern of the weave itself, a pattern where the threads of quantum probability and the threads of spacetime geometry are revealed to be part of the same unified design. This approach has already yielded remarkable fruit, providing powerful new methods for calculating the outcomes of particle collisions that are extraordinarily difficult in standard frameworks. It offers a glimpse of a world where the paradoxes of quantum non-locality and the smooth geometry of relativity might dissolve, seen as different shadows cast by a single, more luminous object. It is a pathway that does not quantize gravity, but rather seeks a geometry from which both quantum theory and gravity naturally crystallize. The elegance of twistors offers a geometry of light, but another framework asks us to build with the atoms of space themselves. Group field theory is the quantum field theory of the cosmos's fundamental grains. We have already encountered the idea that space may be woven from discrete quantum loops or other elementary chunks. But a collection of static building blocks is not yet a dynamic universe. Group field theory provides the missing ingredient, the rules of interaction and combination. It treats these quanta of space not as isolated entities, but as excitations of a quantum field, much like electrons are excitations of the electron field. The key difference is profound. This field does not live on a pre-existing spacetime. Instead, it is defined over an abstract mathematical space called a group manifold, which encodes the possible quantum states of geometry, like the possible shapes and connections a tiny grain of space can have. In this framework, the birth of spacetime is a process of cosmic condensation. Imagine a vast, formless cloud of water vapor. Each water molecule is like a quantum of space jostling randomly. Under the right conditions, these molecules begin to link together, forming droplets, then streams, then a calm, continuous body of water. Group field theory describes a similar phase transition. The fundamental quanta, governed by the field's interactions, begin to bond and entangle in vast numbers. Their individual quantum properties get washed out, and from their collective, coherent behavior, the smooth, classical geometry of spacetime emerges. It is the universe finding its rhythm, moving from a chaotic quantum fog to an ordered, four-dimensional continuum. This approach provides a powerful bridge. It takes the discrete, granular picture of theories like loop quantum gravity and gives it a dynamical language, a way to describe how those grains combine, interact, and ultimately give rise to the stage upon which all other physics plays out. The goal is to derive the equations of general relativity not as fundamental laws, but as the large-scale, statistical description of this underlying quantum system, much like the equations of fluid dynamics emerge from the collective motion of countless atoms. Einstein's theory of general relativity paints gravity as the curvature of a smooth, geometric stage. But what if that stage can not only bend but also twist? This is the fascinating extension known as the Einstein-Cartan theory. In this refined picture, spacetime possesses two distinct geometric qualities, not just one. The first is the familiar curvature, the warping caused by the presence of mass and energy that guides planets along their orbits. The second is a new, more subtle property called torsion. Torsion represents an intrinsic twisting in the fabric of spacetime itself, a kind of microscopic corkscrew geometry that arises not from mass, but from the quantum spin of the fundamental particles that inhabit it. Every electron, every quark, every fermion carries an intrinsic quantum spin, a tiny, fundamental angular momentum as inherent as its electric charge. In Einstein-Cartan theory, this pervasive spin of matter becomes the source for spacetime's torsion. The universe is not just a bent canvas, it is a dynamically twisted one, with every spinning particle giving a tiny, quantum tug on the geometric weave around it. When we then ask how to make this richer geometric picture quantum, something beautiful happens. The promotion of Einstein-Cartan theory to a quantum framework provides a natural, geometric home for fermionic matter. Unlike in standard approaches where matter fields are often added by hand onto a gravitational background, here the spinning particles are woven into the very geometry they help create. This intimate marriage between spin and geometry suggests a profound resolution to one of general relativity's most troubling features, the singularity. In the extreme conditions of a black hole's core or the universe's first moment, where curvature is predicted to become infinite, the effects of torsion may act as a cosmic pressure release valve. The twisting of spacetime could generate a repulsive force that counters the crushing gravitational collapse, preventing the formation of a true, lawless point of infinite density. Instead of a singularity, the universe might experience a bounce or a smooth transition into a new phase. This idea has deep connections to other paths in our map. The quantum version of Einstein-Cartan theory shares a close kinship with loop quantum gravity, as both treat spacetime geometry as a dynamic quantum entity. In cosmological models, this torsion-induced repulsion offers a compelling alternative to cosmic inflation for explaining the universe's large-scale smoothness, suggesting our cosmos may have emerged from a prior contracting phase. It is a vision where the universe's most catastrophic endpoints are softened not by new dimensions or holograms, but by the gentle, intrinsic twist endowed by the spin of every particle within it. Einstein's great insight was the union of space and time into a single, democratic fabric where no direction is privileged. But what if this perfect symmetry is not the final word? Another bold path to quantum gravity suggests that at the deepest levels, time and space are not equal partners. This is Horava-Lifshitz gravity, a proposal that dares to break one of modern physics' most sacred principles, Lorentz invariance. In our everyday world and in all of Einstein's relativity, the laws of physics look the same to all observers moving at constant speed. This symmetry enforces the constancy of the speed of light and binds time and space together as a unified spacetime. Horava-Lifshitz gravity proposes that this beautiful symmetry is not fundamental, but an emergent feature that only appears at the low energies and large scales of our familiar world. At the extreme high-energy realm of the quantum gravity regime, the theory suggests time and space must be treated differently. It gives time a privileged, absolute role, separating it from the spatial dimensions. This radical break from tradition is not done lightly, but for a powerful mathematical reward, renormalizability. By treating time differently, the theory tames the destructive infinities that plague other attempts to quantize gravity, offering a potential path to a complete, calculable quantum theory. The implications are profound. In this framework, the speed of light is not a fundamental constant of nature, but an emergent phenomenon that settles to a fixed value as the universe cools and expands from its fiery beginnings. In the frantic energy of the early cosmos, light could have propagated at vastly different speeds, fundamentally altering the story of cosmic evolution. This could provide novel explanations for the universe's uniformity and structure without relying on the standard inflationary paradigm. It paints a picture of a cosmos whose most fundamental rules are asymmetrical and dynamic, with the smooth, relativistic stage we experience today crystallizing from a more primitive, anisotropic beginning where time itself held a unique and sovereign power. The universe may be written in the language of matrices, not as a science fiction simulation, but as a profound mathematical possibility emerging from the heart of string theory itself. These are matrix models, stripped down, lower-dimensional versions of the full string theory symphony. In these simplified arenas, the fundamental degrees of freedom are not vibrating strings moving through a pre-existing space. Instead, they are abstract mathematical objects, matrices, vast arrays of numbers that obey specific rules of multiplication and addition. At first glance, this seems a world away from geometry, a purely algebraic landscape of equations with no concept of distance, no up or down. Yet, within the dance of these matrices, something miraculous can occur. Under certain conditions, as the matrices interact and their size grows to immense proportions, their collective dynamics can spontaneously generate the very geometry of spacetime. It is as if you gave a supercomputer the task of solving an enormous system of equations that only describe relationships between abstract symbols, and from the solution, a three-dimensional landscape naturally crystallized, complete with its own intrinsic distances and curvature. The matrices, in their complex interplay, become the pixels from which the picture of space is rendered. This makes matrix models invaluable as cosmic toy models, sandboxes where physicists can rigorously test the radical idea that spacetime and gravity are not fundamental. They provide a concrete mathematical playground where one can watch, step by step, how a smooth, geometric universe might emerge from purely algebraic, non-geometric building blocks. In these models, a point in space is not a primary ingredient. It is a derived concept, an approximate label we use to describe a particular pattern of correlations within the vast, interacting matrix. The force of gravity, then, would not be a fundamental interaction but a statistical effect, a consequence of how this underlying matrix system organizes itself. It is a vision where the stage of reality is not assumed but computed, offering a tantalizing glimpse into a universe whose deepest truth is not geometry but algebra. Shape dynamics offers a radical reimagining of Einstein's universe, one built not from the geometry of spacetime but from pure shape. In this profound reformulation, the fundamental symmetry of nature is not the ability to stretch and warp the entire spacetime continuum. Instead, it is the freedom to change the scale of space itself at every point, a spatial conformal transformation, while keeping all angles and proportions perfectly intact. Imagine you have a detailed map of a continent. You can stretch that map in every direction, making the whole continent appear larger or smaller on the page, but you never change the relative distances between cities or the shape of its coastline. That is the core symmetry of shape dynamics. It discards the idea of a universal, ticking clock that exists outside the system. In this view, time is not a fundamental parameter against which change is measured. Time is what we call the sequence of changes in the shape of the entire universe. The only thing that is real, the only thing that truly changes, is the pattern of relationships between all the objects in the cosmos. The universe evolves from one overall shape to another, and we perceive this succession of shapes as the flow of time. This relational notion of time directly confronts one of the deepest puzzles in quantum gravity, the notorious problem of time. In standard approaches, when you try to apply quantum rules to the entire universe, the equations often suggest that nothing changes at all, that the universe is static and frozen. This is because the time variable from general relativity gets swallowed up in the quantum formalism, leaving no external clock to measure evolution. Shape dynamics provides an elegant escape, since time is not an external parameter but is defined by the changing shape of the universe itself. The quantum description naturally describes a universe that is evolving. It is a universe where change is primary and time is the story of that change. This perspective offers a breathtakingly new lens on cosmology. The history of our cosmos is not a movie playing out on a fixed spacetime screen. It is a single, dynamic sculpture that is continuously transforming its own shape. The Big Bang is not an event at a time, but a particular, highly symmetric shape from which all subsequent shapes have unfolded. This framework suggests that the large-scale structure and uniformity we see in the cosmos might be a direct consequence of the universe's journey through its own space of possible shapes, governed by this deep conformal symmetry. It is a vision where the cosmos is not a container for events, but a self-defining, evolving pattern whose only true measure is its own relational form. The universe could be a story written in connections. Another profound idea imagines the fabric of reality not as a smooth sheet or a collection of grains, but as a vast, evolving network, a cosmic web of relationships that is itself the stage. This is the vision of quantum gravity. In this model, the fundamental substance of spacetime is a graph, a mathematical structure of nodes or points connected by links or lines. At the highest energies in the universe's first fiery moments, this graph is a seething chaos. Every node is connected to nearly every other node in a dense, hot tangle of potential. There is no sense of distance, no clear dimension, only a buzzing, over-connected network where any point can instantly influence any other. But as this primordial network cools as the energy drops, it can undergo a dramatic transformation, a phase transition. Think of water freezing into ice. The frantic, liquid dance of molecules gives way to a stable, crystalline lattice. In quantum gravity, something similar happens to the graph of spacetime. The highly connected, disordered network freezes into a new, stable configuration. Most of the countless links between nodes become inactive or break, leaving behind a sparse, regular pattern where each node is connected only to a few nearest neighbors. This new, low-dimensional lattice emerging from the chaos is what we perceive as our smooth, three-dimensional space. The familiar geometry of distance and dimension is not a given. It is a pattern of connectivity that crystallized as the universe cooled. This framework offers a breathtakingly simple origin for dimensionality itself. Why do we experience three spatial dimensions? Because that is the stable, low-energy pattern into which this cosmic graph froze. In a different universe with different rules, the graph might have frozen into a 4-dimensional or 2-dimensional lattice. Our reality's very shape is a memory of that ancient thermodynamic event. This idea naturally connects to other profound concepts on our map. A dynamical graph that processes information sounds remarkably like a quantum computer. In this view, spacetime itself could be seen as the hardware of a cosmic computation, where each node is a quantum bit and each active link is a logical operation. The evolution of the universe from the Big Bang to the formation of galaxies would be the result of this immense natural computation running its course. What we call the passage of time is simply the sequential updating of the network's connections. It transforms our cosmos from a static arena into a dynamic processor, where the laws of physics are the algorithms and the history we see is the output. 17. The deepest connections in the universe may be invisible. We have seen how geometry might emerge from networks, graphs, and algebra. But what if the very glue that binds the cosmos into a coherent whole is the same phenomenon that so baffles us in the quantum realm? What if the fabric of space and time is woven from quantum entanglement itself? This is the radical proposal known as internal relativity or entanglement-based emergence. It suggests that what we perceive as smooth, continuous spacetime is not a foundational stage, but a magnificent illusion arising from the intricate web of quantum correlations between countless fundamental degrees of freedom. In this view, the theory that underlies everything has no inherent geometry, no pre-existing notion of here versus there, no before or after. It is a purely quantum system, a vast collection of interacting parts whose only properties are their quantum states and how they are entangled with one another. From this featureless, non-spatial soup, the geometry of the universe is meant to crystallize. The key insight is a breathtaking redefinition of distance. In our world, two objects are close if you can quickly move from one to the other. But in this fundamental quantum substrate, distance is not a primary concept. Instead, it is defined by the strength of the entanglement between subsystems. Two quantum degrees of freedom are effectively close together in the emergent space if they are highly entangled, sharing strong quantum correlations. They are far apart if they are only weakly entangled or not entangled at all. Locality, the rule that objects can only directly influence their immediate neighbors, is not a law written into the universe's foundation. It is a consequence that emerges when the pattern of entanglement creates a geometry where such local interactions become the most natural description. Think of a vast social network. Two people are not physically close, but if they constantly communicate, share information, and influence each other's decisions, they are effectively close in the network's relational space. The geometry of our social world emerges from these patterns of connection, not from their geographic addresses. In a similar way, internal relativity proposes that the geometry of spacetime is the geometry of the universe's quantum entanglement network. This framework provides a stunning potential resolution to one of general relativity's most profound features, its background independence. Einstein's theory does not play out on a fixed stage. The stage itself is the dynamic actor. Internal relativity achieves this naturally because the emergent spacetime geometry is not imposed from outside. It is dynamically generated by the evolving entanglement pattern of the underlying quantum whole. A change in the entanglement structure, perhaps triggered by a massive object, would directly correspond to a curvature in the emergent spacetime, explaining gravity not as a force, but as a thermodynamic consequence of changing quantum information. This vision transforms our understanding of reality's bedrock. Space is not a container, it is a manifestation of quantum connectedness. The vast distance between stars is not an empty void, but a reflection of the specific, delicate pattern of correlations in the universal quantum state. It suggests that if we could somehow sever the entanglement between two regions of space, they would literally drift apart in the emergent geometry, becoming disconnected universes. In this picture, the Big Bang might mark the moment when a primordial state of total, maximum entanglement began to cool and differentiate, weaving the first threads of spatial separation from a timeless, unified quantum whole. The cosmos is not expanding into anything. It is the ongoing, dynamic reconfiguration of the universe's fundamental quantum relationships. Within the granular world of loop quantum gravity, where space is a network of woven loops, a crucial question remains. How does this quantum geometry change? How does the universe evolve from one quantum state to the next? The answer is found in a beautiful and complex structure known as a spin foam. If the spin network we described earlier is a single, frozen snapshot of space, a moment in time, then a spin foam is the entire film. It is the four-dimensional history, the dynamic story of how that quantum geometry unfolds. Picture the spin network as a vast, intricate spiderweb, each thread representing a quantum of area. Now, imagine that web is not static but alive. As time progresses, the connections in the web change. Threads merge, split, and reconnect in a complex dance. If you could stack every single frame of this dance on top of each other, you would not get a solid block. Instead, you would see a bubbly, effervescent structure, a foam of interlinking surfaces. This is the spin foam, a frothing sea of quantum geometry where each bubble represents a quantum fluctuation of spacetime itself. The foam's intricate architecture encodes every possible way the spin network can transition from one configuration to another. The ultimate goal here is profound. It is to provide a complete sum over history's formulation for quantum gravity. This is a concept borrowed from the legendary physicist Richard Feynman. In quantum mechanics, a particle does not take a single path from point A to point B. Instead, it simultaneously explores every conceivable path, and we calculate its behavior by summing the contributions of all those possible histories. Spin foam models apply this radical idea to the entire universe. They propose that our smooth, classical spacetime does not follow a single, predetermined evolutionary line. Rather, it emerges from the quantum superposition of every possible spin foam, every possible twisting, bubbling, reconnecting history of the quantum geometry. Our reality is the most probable, coherent pattern that rises from this chaotic quantum soup of all possible spacetimes. It is as if the universe's history is not a single thread, but a tapestry woven from the ghostly contributions of countless near misses and alternate possibilities, with our experienced timeline being the one that resonates most strongly from the quantum noise. There is a mathematical art to building universes from the simplest of shapes. While many theories propose a fundamental granularity to space, reg calculus offers a powerful way to approximate Einstein's smooth, curving universe using nothing but flat, geometric blocks. Imagine trying to model the surface of a sphere like our planet using only small, flat triangles. The more triangles you use, the smoother and more spherical your model becomes. Reg calculus applies this brilliant idea to the full four-dimensional fabric of spacetime. It replaces the continuous, curving geometry of general relativity with a vast assembly of flat, four-dimensional blocks called simplices, the higher-dimensional analogues of triangles and tetrahedra. In this piecewise flat universe, all the intricate curvature described by Einstein is not smoothed into every point, but is concentrated entirely at the hinges, the joints where these flat blocks meet. Gravity, in this discrete picture, becomes a kind of deficit angle, a measure of how the geometry must bend at these joints to fit the flat pieces together into a coherent whole. This is more than just a clever approximation scheme. It is a profound conceptual shift. By providing a way to describe gravity without relying on infinitesimal calculus or smooth coordinates, reg calculus suggests that the smooth continuum may be a convenient fiction, a useful approximation to a reality that is, at its heart, built from discrete, chunky elements. Its greatest power, however, lies in computation. by translating the complex, non-linear equations of general relativity into the combinatorial problem of gluing simple blocks together. Reg calculus opens the door for numerical simulations of quantum gravity. This is precisely the engine behind the approach we explored earlier, causal dynamical triangulations. In that framework, the universe's entire history is constructed by summing over every possible way to glue these four-dimensional simplices together, with the crucial rule that cause must always precede effect. Reg calculus provides the precise geometric language to calculate the action, the probability weight, for each of these myriad triangular universes in that grand quantum sum. It transforms an abstract quantum principle into a concrete, computable model of spacetime's emergence. So while it may have begun as a numerical tool, Reg calculus stands as a quiet testament to a powerful idea, that the universe's majestic curvature might ultimately be understood as the collective effect of countless flat, geometric facts fitting together in just the right way. Einstein's curved spacetime is a masterpiece, but it is not the only way to tell gravity's story. There exists a completely equivalent, yet philosophically distinct, description where gravity is not geometry but a true force. This is teleparallel gravity. In this framework, the stage of the universe is not a warped dynamic fabric. Instead, it remains perfectly flat, the immutable arena of special relativity. So what causes planets to orbit and apples to fall? The answer lies in a property called torsion, a kind of intrinsic twisting in how the flat spacetime is connected from point to point. Imagine two hikers starting at the equator, both walking due north. In a curved geometry like Earth's surface, their paths will slowly converge, and they might eventually meet at the North Pole. That is the picture of general relativity. In teleparallel gravity, the surface itself is perfectly flat, like an infinite plane. The hikers still converge, not because the ground bends, but because an invisible force field gently twists their paths, pulling them together as they walk. The mathematical predictions are identical, but the story is fundamentally different. Gravity is not a consequence of curved geometry. It is a force mediated by a field that lives on a flat stage. This shift in perspective offers intriguing advantages when we ask the quantum question. In the standard approach, quantizing geometry is notoriously difficult. But quantizing a force field on a fixed background is a problem physicists have solved before with the other fundamental forces. Teleparallel gravity reframes the challenge, turning gravity into something that looks more like the other forces we already know how to quantize. Furthermore, this framework provides a natural and elegant home for fermions, the particles like electrons and quarks that carry intrinsic spin. In teleparallel gravity, the spin of matter couples directly and neatly to the torsion of the spacetime connections. This creates a more symmetrical and potentially simpler marriage between matter and gravity at the quantum level. It is a reminder that sometimes the deepest mysteries can be approached by rewriting the story in a completely new language, one where the universe's flat, timeless stage remains and gravity becomes a familiar actor upon it. Einstein's equations are profoundly local, a beautiful and strict rulebook where the curvature of spacetime at any point is determined solely by the matter and energy right there, at that exact location. But what if gravity has a memory or a kind of far-sightedness? This is the radical proposition of non-local gravity, where the gravitational influence at one point depends on the geometry of distant regions or even on the entire history of the universe. It is as if the fabric of spacetime does not just react to the weight placed upon it now, but also remembers every weight that has ever been placed upon it, with those memories subtly shaping its present tension. This idea is not a rejection of Einstein's vision, but an inspired extension, often emerging naturally from attempts to include quantum effects. When you try to blend quantum fluctuations with gravity, the calculations often produce terms that reach across space and time, suggesting that the smooth, local picture of general relativity might be an approximation that breaks down when the full quantum story is told. One of the most compelling consequences of this non-local reach is its power to heal the universe's most violent wounds. In the standard picture, black holes contain a point of infinite density, a singularity where the laws of physics cease to make sense. But in certain non-local theories, the gravitational influence of the entire mass of the black hole, spread across its history, can act to smooth out that infinite spike. The singularity dissolves, replaced by a region of extreme but finite density, like a storm that is fierce but ultimately containable. Similarly, the mysterious force accelerating the expansion of the universe, dark energy, might find an elegant explanation. Instead of requiring a new, exotic form of energy permeating the cosmos, non-local modifications to gravity could naturally generate a repulsive effect on cosmic scales. The accumulated memory of the universe's past expansion, woven into the geometry of the present, could be pushing galaxies apart. This offers a breathtaking alternative, suggesting dark energy is not a substance, but a ghostly echo of the cosmos's own history, written into the non-local fabric of gravity itself. Yet this profound idea carries a profound challenge. If gravity can reach across vast distances instantaneously, how do we protect the sacred rule of causality, that cause must always precede effect? If the sun were to vanish, would we feel its gravitational absence immediately, breaking the universal speed limit of light? The resolution lies in the subtle mathematics. In the most carefully constructed non-local theories, the non-locality is not a simple, faster-than-light signal. It is an integral part of the geometry's equilibrium, a holistic condition that respects the causal structure of spacetime. The influence is not a message sent from a to-be, but a global property of the entire system, determined all at once, like the final shape of a tensioned net being determined by every pull on its edges simultaneously. It is a delicate dance, maintaining the unbreakable chain of cause and effect while allowing the universe to act as a coherent, interconnected whole, where every part remembers and is shaped by the story of the whole. Gravity's reach seems infinite, a whisper that never truly fades across the cosmic void. Yet one daring question challenges this sacred tenet of Einstein's theory. What if the graviton, the hypothetical quantum particle of gravity, is not massless but has a tiny, almost imperceptible mass? This is the radical proposition of massive gravity. In our standard picture, the graviton's lack of mass is what allows the gravitational force to stretch across billions of light years, binding galaxies into a vast cosmic web. Giving it even a minuscule mass would fundamentally change the rules. It would introduce a cutoff, a finite range beyond which gravity's influence would decay exponentially, like a radio signal fading into static. On the surface, this idea seems heretical, a direct assault on one of general relativity's core successes, but its motivation is profound. A massive graviton could naturally explain the universe's accelerating expansion without invoking the mysterious dark energy. If gravity weakens more than expected on the very largest scales, the cohesive pull holding the cosmic structure together would diminish, allowing space itself to push apart more easily. It is an elegant trade, swapping one cosmic mystery for a radical modification of our most trusted force. For decades, however, this elegant idea was plagued by a fatal mathematical flaw known as the Boulware-Desir ghost. This was not a spectral phantom, but a destructive instability, an unwanted, unphysical mode that would appear in the equations and cause probabilities to run amok, rendering any theory of massive gravity nonsensical and unpredictable. It was a seemingly insurmountable barrier, consigning the concept to the theoretical wilderness for generations. Then, in a stunning breakthrough in the early 2010s, a series of papers by physicists Claudia de Ram, Gregory Gabadadze, and Andrew Tolley cracked the code. They constructed a sophisticated, multi-layered structure of mathematical terms, a delicate interplay of interactions that precisely cancelled out the ghostly instability at every level. This DRGT massive gravity, as it is known, provided the first consistent theoretical framework where the graviton could have a mass without the universe descending into mathematical chaos. The implications are as observable as they are strange. In our solar system, where gravity is strong and distances are relatively small, a massive graviton's effects would be utterly negligible, preserving all of Einstein's confirmed predictions. But on the vast cosmological stage, the modifications could become dramatic. The cosmic acceleration we attribute to dark energy might instead be a sign that gravity is gently fading at the grandest distances. Furthermore, the gravitational waves rippling through spacetime from colliding black holes would travel at a speed slightly less than that of light, a subtle fingerprint that future, exquisitely sensitive detectors might one day discern. This framework transforms the graviton from a silent, weightless carrier of curvature into a particle with a tangible, if tiny, presence, offering a universe where the force that shapes the cosmos has a limited, though still astronomically vast, domain of influence. The stage of reality may not be a singular, immutable fabric. What if our universe is woven from two distinct yet intertwined geometries? This is the elegant and complex world of bimetric gravity. In this framework, Einstein's single metric tensor, the mathematical object that defines distances and the flow of time, is joined by a second, independent metric. Think of it as two separate maps of the same territory, each with its own scale and contour lines superimposed upon one another. These two geometries are not just mathematical abstractions, they have distinct physical roles. One metric couples directly to all the matter and energy in the universe, the stars, planets, and even us. It defines the spacetime we actually move through and experience, the stage upon which our physical lives play out. The second metric is a hidden dynamical field, a kind of shadow geometry that does not directly interact with ordinary matter, but interacts powerfully with its twin. The two metrics talk to each other through a specific interaction term, a set of mathematical rules that dictates how they influence each other's curvature and evolution. This elegant doubling of geometry offers profound solutions to the universe's greatest puzzles. The mysterious force accelerating cosmic expansion, dark energy, finds a natural home here. The interaction between the two metrics can generate a constant, repulsive pressure on cosmological scales, driving galaxies apart without the need for any exotic, invisible energy fluid. It is as if the hidden geometry acts as a kind of cosmic spring, pushing against the fabric we experience. Even more strikingly, bimetric gravity can offer an alternative explanation for the other great cosmic mystery, dark matter. The gravitational effects we attribute to vast halos of invisible matter holding galaxies together might instead be a consequence of the way the two geometries interact in regions of low density. The hidden metric modifies the dynamics of gravity itself, creating the illusion of extra mass where there is none. In this view, a galaxy's rotation curve, which famously stays flat instead of falling off, is not evidence of unseen particles, but a fingerprint of this dual geometric dance. It suggests that the cosmos is not mostly made of unknown stuff, but is governed by a richer, more complex gravitational law than Einstein envisioned. This framework demands a delicate balance. The mathematics must carefully avoid instabilities and ghosts, but when constructed precisely, it paints a universe of breathtaking depth, a cosmic dialogue between two intersecting realities where the force we feel is the echo of a conversation happening just behind the veil of our perception. Symmetry is the hidden language of the cosmos, a principle that reveals deep connections where we once saw only separation. Among the most powerful of these symmetries is supersymmetry, a theoretical proposal that for every known particle of matter, like an electron or quark, there exists a superpartner particle of force and vice versa. It is a profound pairing that would weave the two great families of the quantum world into a single, harmonious tapestry. When we take this elegant symmetry and apply it directly to the geometry of Einstein's general relativity, something magnificent emerges, a theory of breathtaking beauty called supergravity. This framework does not merely add gravity to the particle zoo, it geometrizes the entire supersymmetric ensemble. In supergravity, the superpartners of the graviton, known as gravitinos, are not separate entities awkwardly glued onto spacetime. They are natural extensions of the geometry itself, just as the curvature of spacetime is the geometric manifestation of the ordinary graviton. This provides a stunningly unified picture where gravity and the other forces are not just neighbors in a quantum field, but different facets of a single, richer geometric object. The force we feel and the matter we are made of become different vibrational modes of a supersymmetric spacetime. It is as if the universe's symphony, which we previously heard in two distinct sections, one for strings and one for winds, was suddenly revealed to be written for a single, grand orchestra where every instrument has a complementary partner, creating chords of unimaginable harmony. This geometric elegance makes supergravity more than a standalone idea. It is the inevitable low-energy whisper of the full-string theory symphony. When the vibrating strings of that grander theory settle into their lowest energy states, the resulting description of our large-scale world is precisely that of supergravity. This gives the theory immense power as a crucial testing ground. Because it is simpler than the full 10-dimensional complexity of strings, physicists can use supergravity to explore deep questions about quantum black holes, the holographic principle, and the very nature of information in spacetime. Calculations in supergravity have been instrumental in verifying the AD-SCFT correspondence, providing concrete evidence that a theory of gravity in a bulk space can be perfectly equivalent to a quantum theory on its boundary. In this way, supergravity acts as a brilliant bridge, a manageable arena where the wild, conceptual promises of strings and holography meet the hard, testable ground of mathematical physics. It stands as a testament to the power of symmetry, suggesting that the universe's deepest law may not be a force or a particle, but a pattern of relationships so beautiful that from it, everything we know must inevitably unfold. The most radical ideas on our map dare to erase the stage entirely. This is the realm of pregeometry, a class of theories that declares space, time, and even geometry itself to be illusions, latecomers to the cosmic story. Here, the fundamental theory is not about things moving in a container. It is built from something deeper, more abstract, and utterly non-spatial, pure algebra, raw combinatorics, or the pristine logic of cause and effect. The world we experience is meant to crystallize from this featureless substrate, much like the warmth of a room emerges not from a substance called heat, but from the frantic, invisible dance of countless molecules. Temperature is a useful, emergent concept, but it is not fundamental. Pregeometry argues that space and time are the same collective phenomena that only make sense in a suitable limit, when a vast number of these underlying, non-geometric elements interact in just the right way. Think of a perfectly clear image on a digital screen. Up close, you see it is not a continuous picture at all, but a grid of individual colored pixels, each one just a number in a computer's memory. The image, with its shapes and depth, emerges from the pattern and relationships between those abstract data points. Pregeometry suggests our universe is that image, and the pixels are something far stranger than tiny dots in space. They are mathematical relationships with no inherent location. In some proposals, the building blocks are purely algebraic operations, the kind of symbolic manipulations you might perform in a high-level math class, utterly divorced from any notion of distance or duration. In others, the universe begins as a vast, evolving network of logical propositions, a cosmic if-then statement generating more if-then statements, from which the geometry of paths and connections slowly congeals. The force of gravity, in this view, would not be a fundamental interaction. It would be a statistical tendency, a thermodynamic effect arising from this underlying system's drive toward equilibrium, a side effect of the way information gets organized. This flips the entire problem of quantum gravity on its head. Instead of struggling to quantize the geometry of spacetime, the task becomes to discover what kind of timeless, spaceless, logical or algebraic system could possibly give rise to something that looks at a large scale, exactly like Einstein's curved continuum. It is the ultimate reduction, seeking not the atoms of space, but the atoms of existence from which the very idea of where and when are born. The universe's deepest structure may be written not in geometry, but in bits. A revolutionary perspective is gathering momentum, one that sees the principles of quantum information theory as the true bedrock of reality, with gravity itself emerging from their dance. This viewpoint transforms entanglement, entropy, and computation from useful tools into the fundamental threads from which spacetime is woven. At its heart is a stunningly simple yet profound equation, ER equals EPR. This is not a formula from a textbook, but a conjecture that links two of the 20th century's greatest insights. On one side stands EPR, named for Einstein, Podolsky, and Rosen, representing the spooky action at a distance of quantum entanglement, where two particles remain mysteriously connected regardless of the distance between them. On the other side is ER for Einstein and Rosen, representing the microscopic wormholes or Einstein-Rosen bridges that are threaded through the fabric of spacetime in general relativity. The conjecture boldly proposes that these two seemingly different phenomena are, in fact, one and the same. A pair of entangled particles, like two electrons spinning in perfect sync across the galaxy, are not just correlated. They are physically connected by a minuscule, non-traversable wormhole, a Planck-scale tunnel in the geometry of spacetime. What we call quantum entanglement is the information-theoretic signature of a geometric bridge too tiny to see. This idea flips our understanding completely. It suggests that the connectivity of space, the very fact that one point can influence another, is not a primitive given. It is built up from countless such quantum information links. Space is not a container for entanglement. Space emerges because of entanglement. To build a universe, you start with a vast number of quantum bits or qubits and entangle them in a specific, intricate pattern. As the density and complexity of these entanglements grow, they stitch together into a coherent geometry. A region of space where entanglement is dense and strong appears to us as a smooth, continuous fabric. A region where entanglement is weak or absent appears as a vast, empty chasm. This perspective provides a breathtakingly elegant explanation for the holographic principle. The information describing a three-dimensional volume is stored on its two-dimensional boundary because that boundary is where the web of entanglement that constructs the interior finds its anchor points. Even the force of gravity is reinterpreted. An object's gravitational pull could be understood as the way its mass distorts the underlying pattern of entanglement in its vicinity, creating a statistical tendency for other objects to move toward the region of higher entanglement density. It is as if the universe is a cosmic quantum computer, and spacetime is the hardware that emerges from its ongoing calculation. The fabric we walk upon is not a stage, but a living, dynamic network of quantum connections, and every gravitational field is a gentle tug in the pattern of its weave. The attempt to apply quantum rules to the cosmos itself leads to one of the most profound and puzzling equations ever written. In the 1960s, physicists John Wheeler and Bryce-DeWitt took a monumental step, daring to treat the entire universe as a single quantum object. Their resulting equation, the Wheeler-DeWitt equation, is the Schrödinger equation for all of reality. It does not describe the evolution of particles within space and time. Instead, its variable is the wave function of the universe, a mathematical object that encodes the probability amplitude for every possible three-dimensional geometry the cosmos could have. This is a staggering concept, a single quantum state that contains, in superposition, every possible shape and size of space, from a smooth, expanding cosmos to a wildly crumpled, chaotic foam. Yet this breathtaking ambition comes with a conceptual shock that has echoed through theoretical physics for decades. The Wheeler-DeWitt equation is timeless. The familiar time variable, the t that ticks in every other equation of physics, simply vanishes from it. The equation describes a static landscape of possibilities, a frozen quantum snapshot. It tells us the universe just is, in a quantum sense, but it provides no mechanism for change, for the dynamic flow from one moment to the next that is the essence of our lived experience. This is the notorious problem of time, a central paradox in canonical quantum gravity. If the fundamental equation of the cosmos lacks time, then where does our powerful, undeniable experience of past, present, and future come from? One compelling interpretation is that time is not a fundamental ingredient, but an emergent property, a story we tell about the changing relationships between things within the universe. Think of a timeless, unchanging movie reel containing every single frame of a film. The experience of watching the movie unfold, the feeling of time passing, only happens when a projector runs the reel, creating the illusion of motion from a sequence of still images. In this view, the Wheeler-DeWitt equation provides the reel, the complete set of all possible cosmic frames. Our experience of time is the projector, a phenomenon that emerges from the way we, as complex subsystems within the universe, interact with and measure one particular sequence of these frames. We do not move through time, we are patterns that persist across the succession of these frozen geometries, and we call that persistence the flow of time. While the Wheeler-DeWitt equation itself is incomplete, a challenging mathematical puzzle that is difficult to solve and interpret, its legacy is immense. It stands as the foundational cornerstone of the canonical approach to quantum gravity, a bold and rigorous attempt to quantize Einstein's geometry directly. It forced physicists to confront the deepest questions about the nature of reality. Is time fundamental, or is it, like temperature, a useful concept that only makes sense for a large, complex system? The equation's silent, timeless landscape continues to challenge and inspire, a reminder that in the quest to understand quantum gravity, we may have to relinquish our most basic intuitions about the stage upon which we believe our lives are performed. The timeless landscape of the Wheeler-DeWitt equation presents a profound challenge. How do we calculate the probabilities for the universe's quantum geometry if time itself is not a variable? Stephen Hawking offered a breathtakingly clever mathematical escape, one that transforms the problem into a different kind of space entirely. He proposed that we treat time not as a real, flowing quantity, but as an imaginary dimension. This is not a flight of fancy, but a precise mathematical trick. By making this substitution, the familiar dynamic spacetime of general relativity, with its light cones and causal structure, morphs into a static, four-dimensional geometric shape, a purely spatial object. This is the realm of Euclidean quantum gravity, named for the ancient geometer Euclid, because in this picture, the universe's history becomes a closed, finite shape without any singular edges or boundaries. Hawking's great insight was to apply Richard Feynman's path-integral approach to this timeless geometry. Feynman taught us that a quantum particle explores every possible path between 2 points. Hawking applied this to the entire cosmos. In the Euclidean formalism, the quantum amplitude for the universe to have a particular large-scale geometry is calculated by summing over all possible four-dimensional shapes, all the smooth, closed surfaces that could connect to that final configuration. It is a sum over histories, but these histories are not timelines, they are shapes. This mathematical machinery, for all its strangeness, yielded two of the most stunning results in modern theoretical physics. The first was Hawking radiation. By studying the behavior of quantum fields on the Euclidean version of a black hole geometry, Hawking discovered that black holes are not truly black. They must glow with a faint thermal heat slowly evaporating over astronomical eons. This revelation forever linked gravity, quantum mechanics, and thermodynamics. The second, even more profound result was the no-boundary proposal for the origin of the universe. In the standard Big Bang picture, the cosmos begins in a singularity, a point of infinite density where the laws of physics break down. Hawking and James Hartle asked what shape the Euclidean path integral would favor at the very beginning. Their answer was elegant and radical. They proposed that if you trace the universe's history back in imaginary time, you would not find a sharp, singular starting point. Instead, you would find that the four-dimensional geometry smoothly rounds off like the south pole of a globe. There is no boundary, no edge, no before. The question of what happened before the Big Bang becomes as meaningless as asking what is south of the South Pole. In this view, the universe simply is a self-contained, finite geometry where time, as we know it, emerges naturally from the shape. Yet this powerful picture is not without its deep conceptual puzzles. What does it mean for time to be imaginary? We experience time as real and flowing, not as a mathematical abstraction. The Euclidean approach provides spectacularly successful tools for calculation, but the interpretation of those calculations, the translation back to our lived reality of cause and effect, remains one of the most subtle and debated frontiers in all of physics. It offers a universe without a beginning in time, but with a beginning of time, a closed, complete object from which our entire expanding, dynamic history unfolds like a story read from a timeless book. Our own perception carves reality from an infinite cosmos. Every observation, every measurement you make is limited by the finite speed of light and the finite span of a lifetime. You cannot see beyond the cosmic horizon, the farthest distance from which light has had time to reach you since the beginning. This simple, profound fact leads to a radical principle in quantum gravity called causal patch cosmology. It proposes that the only part of the universe that is physically real and describable by a consistent quantum theory is the region that is causally connected to a single observer. This is your causal patch, the bubble of spacetime where events can, in principle, influence you or be influenced by you. Everything outside that bubble, no matter how grand or strange, is fundamentally irrelevant to your quantum description of reality. It is not that distant galaxies do not exist, but that they exist in a different, separate quantum context, like chapters in a book you have not yet read. This idea finds deep roots in the holographic principle, which taught us that all the information within a volume is encoded on its boundary. For a single observer, the relevant boundary is their own cosmic horizon, the edge of their causal patch. The entire universe, in all its possible chaotic splendor, is reduced for that observer to a finite, self-contained quantum system defined by the information on their personal horizon. This perspective offers a powerful solution to one of cosmology's most vexing puzzles, the measure problem of eternal inflation. In some models, inflation is not a one-time event but an eternal process, spawning an infinite number of bubble universes with wildly different properties. In an infinite multiverse, how do we calculate the probability of anything, including why our universe has the constants we observe? Any outcome, no matter how unlikely, will occur an infinite number of times, making meaningful probability calculations impossible. Causal patch cosmology cuts through this infinite confusion with a simple, elegant rule. An observer does not sample from the entire infinite multiverse. They sample only from the finite history of their own causal patch, the beginning of their patch, perhaps a nucleation event from the inflating background, provides a natural starting point for the quantum story. The evolution of that patch from its origin to its final state is a finite, computable quantum gravity process. Probabilities are now well defined because you are asking about the likelihood of sequences of events within a single, finite quantum history. It transforms the problem of explaining our universe from a statistical nightmare over an infinite ensemble into a question of dynamics within one self-contained quantum system. Your reality, the only one you can ever verify, is not the entire multiverse. It is this single, shimmering bubble of causality, a story written on the inside of your own horizon, where every piece of information is, in principle, accessible to you. The infinite cosmos beyond may be real, but for the theory of your world, it is quantum noise, a background of possibilities that never coalesce into the actual events of your lived experience. The search for a single, elegant theory of everything might lead us to a startlingly different destination. Our 30th and final theory is not a specific equation, but a profound and controversial consequence that arises from the mathematics of string theory itself. It suggests that the ultimate laws of nature may not be unique. Instead, the equations could allow for a staggering number of stable solutions, perhaps 10 to the power of 500 or more. This unimaginable variety is known as the string theory landscape. Each point in this landscape represents a possible way for the extra dimensions to curl up and stabilize, and each distinct configuration yields a different set of physical laws and fundamental constants for its universe. The force of electromagnetism could be stronger, the mass of the electron lighter, or the cosmological constant vastly different. In this picture, our universe, with its specific, finely tuned parameters that allow for stars, planets, and life, is just one possibility among a near infinity of others. This landscape naturally gives rise to the concept of the multiverse. If eternal inflation or other cosmological mechanisms are at play, each of these possible vacuum states could be realized in a separate, causally disconnected bubble universe. We do not inhabit a special cosmos with uniquely determined laws. We simply live in one bubble within a frothing cosmic sea where every conceivable set of physics is realized somewhere. This idea solves one profound puzzle, the anthropic principle, which asks why our constants seem so perfectly adjusted for complexity. The answer becomes simple: in a landscape of all possibilities, we can only exist in the rare bubbles where the constants allow for observers like us to arise. Yet this breathtaking vision poses the greatest challenge to the scientific method itself. If every possible outcome exists somewhere in the multiverse, how can we ever make a unique, testable prediction from our fundamental theories? Any observation we make could be explained as mere environmental selection within our particular bubble, rather than a deep clue to a unique underlying law. The quest for quantum gravity thus reaches a philosophical frontier, asking whether the final theory will describe a single, beautiful universe or an endless, untestable tapestry of all possible worlds. 30 paths converge on a single, staggering truth. We have wandered through a forest of ideas, from vibrating strings and granular loops to holographic projections and emergent networks. Each theory is a masterpiece of imagination, a self-consistent universe built from pure logic and mathematics. Yet they cannot all be true, at least not in the way we currently understand them. Stepping back, we see the landscape of quantum gravity is defined by a few great competing paradigms, each offering a fundamentally different answer to the question, what is reality made of? On one side stands the majestic cathedral of string theory and its relatives, proposing that the fundamental objects are not points but strings or membranes vibrating in a reality with more dimensions than we can see. It is a top-down vision of breathtaking unity, aiming to be a final theory of everything from the outset. On the other side, approaches like loop quantum gravity and causal set theory build from the bottom up. They take our familiar four-dimensional world and ask what its quantum atoms might be, suggesting that space and time themselves are not smooth and continuous but discrete and relational. Here, gravity is not unified with other forces by adding ingredients, but by reimagining the stage itself as a quantum object. These are not minor disagreements. They represent a deep philosophical divide about the nature of scientific explanation. Is the universe described by a single, elegant equation from which all else flows? Or does our reality emerge, like the wetness of water or the flow of time, from the collective behavior of countless simpler parts? Despite this grand competition, astonishing common ground has been discovered in the trenches of calculation. Themes echo across the theoretical divide. The concept of emergence has become central, the idea that space, time, and even gravity itself may not be fundamental, but may arise like a wave from a deeper, non-spatial sea of quantum information or relationships. The holographic principle, born from black hole thermodynamics, now influences almost every approach, suggesting that our three-dimensional experience is a projection from a two-dimensional reality. And everywhere, information has become the new currency of physics. Entanglement is no longer just a quantum curiosity. It is now seen by many as the literal glue that binds space together, the thread from which the fabric of spacetime is woven. This convergence is a powerful clue, hinting that while the mathematical languages differ, they may all be describing different facets of the same profound truth. Yet for all this intellectual triumph, a sobering silence echoes from our laboratories and telescopes. Not a single one of these beautiful ideas has yet produced a clear, testable prediction that can be verified or falsified by experiment. The energy scales required to probe the Planck length, where these quantum gravitational effects should become dramatic, are a staggering 15 orders of magnitude beyond what our most powerful particle colliders can reach. It is the difference between the energy of a flying mosquito and the total energy output of the sun. So how do we move forward? The search has become a kind of cosmic detective work, looking for indirect fingerprints in the only laboratory we have, the universe itself. Physicists scrutinize the faint afterglow of the Big Bang for imprints of primordial gravitational waves that might reveal signatures of inflation, a process possibly tied to quantum gravity. They analyze the precise orbits of stars around our galaxy's central black hole, searching for deviations that could hint at a breakdown of Einstein's equations in extreme gravity. They listen intently to the chirps of colliding black holes detected by LIGO and Virgo, searching for echoes or anomalies in the gravitational waves that might betray the quantum structure of spacetime. And they use the mathematics of these theories as guides to understand other frontiers, like the behavior of exotic states of matter, turning the abstract quest for quantum gravity into a tool for discovery here and now. The journey is far from over. We are mapping the territory of possibility, guided by the twin lights of mathematical consistency and the stubborn, beautiful details of the world we actually observe. The final theory, when it comes, will not merely be a set of equations. It will be a new story about what we are and where and when, written in the language of a reality more strange and wonderful than we have yet dared to dream. This grand map of possibilities is more than a collection of equations. It is a testament to the human mind's relentless drive to understand its home. Each of these 30 windows offers a different glimpse into what might lie beneath the skin of reality, from the silent music of strings to the quantum hum of spacetime's own atoms. They represent not a failure to find one answer, but the breathtaking fertility of a question that strikes at the very foundation of physics, the quest to make peace between the infinitely small and the infinitely vast. What unites them all is a single, unifying goal: to weave the probabilistic rules of the quantum world seamlessly into the geometric story of the cosmos, to find the one reality that speaks both languages fluently. The journey is far from a solitary academic exercise. It is a collective adventure spanning generations, where every elegant proof and every stubborn paradox brings us closer to a new chapter in our cosmic story. And while the theories live in the realm of mathematics for now, the universe itself holds the final exam. The coming era of discovery promises to turn speculation into evidence. Exquisitely sensitive gravitational wave observatories will listen for the faintest whispers from colliding neutron stars and black holes, hunting for subtle deviations that could reveal the granularity of spacetime. Precision maps of the cosmic microwave background, the ancient light from the universe's infancy, may contain frozen imprints of quantum gravitational effects from the first fleeting moments. Even tabletop experiments probing the frontiers of quantum mechanics could uncover hints of spacetime's underlying structure. We stand at the threshold where pure thought meets observable reality. The path forward is lit by both the brilliance of theory and the patient gaze of observation. So we turn the question to you as fellow explorers on this journey. Which of these paths resonates most deeply with your sense of how the universe might work? Does the elegance of vibrating strings speak to you, or the stark simplicity of a universe built from causal connections? The conversation is just beginning, and every new perspective adds to the map. The greatest discovery awaits not in a single equation, but in the moment we finally learn to see the world through the eyes of quantum gravity.